Welcome everybody to the AI plus X Dialogue. It is my great pleasure to have you here with an amazing faculty from the AI Center, from the Department of Civil, Environmental, and Geomatic Engineering. And my name is Chris Lubkeman. I am the head of the Strategic Foresight Hub at the ETH in Zurich. The AI plus X series consists of three components. There's a spotlight, a lab, and a dialogue. And this is a collaboration between the AI Center and the Strategic Foresight Hub, where we're trying to help us, our friends, our families, our citizens understand a little bit more about the combination of AI, artificial intelligence, and a topic. And I'm really excited today to be speaking with one of our faculty member who's in a domain where I spent quite a few years personally, professionally, with the built environment and hearing a lot about what is coming. So for those who haven't yet met Professor Fink, Olga Fink, I would encourage you to watch her spotlight, which is on the AI Center webpage, and you can see a lot more about what she's going to be talking about with me and us this afternoon. You are welcome to send in questions. Just send them into the chat, and either I or Fiona will pick them up, and we're going to integrate them into our conversation. So with that, welcome, Olga.
Thank you very much, Chris, and thank you very much for everyone who joined today. So I'm very much looking to the discussion and to the questions and to sharing some of the research that we have been doing with you.
Fantastic. So first of all, did I get your department right? So you're a professor of...
I'm professor of intelligent maintenance systems.
Okay.
So we are developing intelligent algorithms that are able to detect faults, but then once the faults are detected, to distinguish between different fault types, and ultimately also to predict what's the remaining useful life, so when the system are actually going to fail. And one of the on top tasks that we are also performing is to prescribe optimal operation, because once we know how the system condition is going to evolve over time, we can actually use this information and then to recommend what are the optimal operating parameters in order to prolong the remaining useful life, for example, to complete the mission or to return to the workshop.
And so just right on that right there, I think to myself, in so many things, experience and sort of explicit knowledge or explicit knowledge about systems comes into play. So, but you're not working necessarily with explicit, tacit, implicit knowledge, or is that something that's also part of your work with intelligent systems?
Well, we do for example, is we provide decision support to decision makers. But in terms of knowledge, we learn kind of implicitly what are the underlying processes, but partly we don't learn them explicitly. So there we have kind of this implicit learning of the concepts versus explicit learning of the concepts. I'm not sure if this was something that you were referring to with the explicitly learning something or implicitly. But for example, particularly for the degradation processes, we learn them. We learn how the systems degrade, but then it's difficult then to extract what's the underlying degradation processes.
Okay. That's good. I was just sort of imagining this crusty old man or woman going, yeah, you know, I know better than some old algorithm. What's she going to tell me? Right. And that's what I was kind of inferring there.
Well, that happens as well. It did not happen to us, but what we actually, we use domain expertise as a feedback. So for example, what we often do is that we perform predictions, then we share them with the domain experts, and then we get feedback. Was it a correct prediction? But also, for example, what was the fault type? Because what we are often lacking are examples of faults, but also labels for the faults. So this is how we work with domain experts. But then also, yes, we also have, there was an anecdote, it was not from us, but it was from another research group. So they developed a model, I believe it was for a coffee plant. And then they put it in and they predicted when the system is going to fail. And then, so the operators actually went on exactly that point in time, and they were waiting that the system is would be going to fail. And then what happened, obviously, it did not fail at exactly that point in time, and the domain experts were happy that they were right and the algorithm was wrong. So what that research group did afterwards, and they designed a model where they integrated, the domain experts in the development, and also collected their feedback and tried to integrate that in the model, and the acceptance then increased quite a lot. So they did not go afterwards and waited until it failed.
I can just imagine someone there with a wrench or something going, okay. But that's because I know you talk quite a bit, and you are very passionate about these two words, which are decision support, and how your tools and what your research is evolving to help make better decisions. So, am I interpreting that correctly, or
yes,
not?
absolutely. So that is one of the layers of what we actually do, because once we predicted when the components are going to fail, we also need to combine that at higher levels, but also to integrate that with additional operational constraints, for example. But then also we need to provide support to the decision makers. So what can they actually do with those predictions? And one of the questions is also, which additional information can we provide to the decision makers so that they try the model, they trust the models actually more. This has been going in the direction of physics-based or hybrid models, where actually the decision makers trust more when they are provided additional information, when the information is coming from a physical model that they're already familiar with working. But some other researchers were also working with explainable artificial intelligence, where it can be at least pinpoint what were the biggest influencers that resulted in that decision, so that they can also start trusting more to that system or to that algorithm, and then really perform the recommended actions or the recommended decisions.
So can you give me can you help me understand that more in a very concrete way, or steel, or you pick your material or whatever? But I mean, I love concrete, so that's my own problem. But so I mean, kind of help me and those who are listening understand on a real life example, some of the research project right now, because I'm gonna ask you a whole bunch about other ones, but just give us so we can nibble on that a tiny bit.
So one of the decision support systems that we were working on was for tunnel boring machines. And the question there is, so how to, for the operators, how to set the parameters in an optimal way. And typically the experienced ones and the skilled ones are quite good in setting those parameters. But obviously there's quite a lot of uncertainty, and particularly the novices who may not have that much experience, they may not set the parameters in the optimal way. So the project that we were performing there was to learn from the good operators, and then to provide or to apply then this algorithm, provide the recommendations for the operators that may not set the best parameters. So kind of transferring the knowledge that is difficult also to formalize and to put into rules, and then to transfer this to someone who is less experienced and who may need support, particularly for some very uncertain situations that they haven't experienced yet.
So we're talking like 6 parameters, 60, 600? How? Just give me a general. I'm just trying to get my head around. I'm thinking about this
in the order of 10.
Of 10 parameters. Yeah. So could be speed, rotation, things like this, where
Yes.
a human might have a good feeling for it. And then, and so when you're doing your research, you have to acquire the information, or the AI. So you use a lot of sensors to do this, I'm assuming.
Yes.
Right. So what are the kinds of sensors which you're using in your research, and why?
So typically, we only start when the data is recorded already, or when the data is available. So typically, we collaborate with industrial partners for that, and then we analyze their data. But recently, we also started a collaboration with a colleague from the ETA department on monitoring circuit breakers. And this is the first project that where we are involved in selecting the sensors, but also installing them, collecting the data, but then also waiting until the system fails. So we currently have an ongoing master thesis, and we are still waiting for the system to fail. Apparently, it's quite a reliable one, so we really need a while. So that's one of the challenges that we are facing, that there are not so many folds to learn from. So we need to find ways on how to circumvent it. But the type of sensing device, or the type of kind of data collected that we work on include acoustic monitoring, vibration data, temperature, pressure. So different types of sensors, and typically they are not. So it's not just a single sensor that is applied, but it's multiple and different sensors. So that is then also a challenge, and partly it's also, for example, image data that could be collected that we need to integrate as well. So it's multi-model learning that we need to apply to the different types of problems that we are trying to solve.
So are you also using artificial intelligence to, like, if you'll clean the data, to understand the data, or is it mostly trying to understand the implications of the data? I'm just, this is purely a personal question. I'm curious.
What do you mean? Because if we understand the data, that also helps us to understand and to solve the problem. So,
Sure.
but typically for the data cleaning, that will be rather kind of the standard processing algorithm, partly also signal processing.
Right.
And then, well, we apply machine learning algorithm when we need some learning behind it. So
sometimes in a data set, an anomaly can be garbage, and sometimes the anomaly can actually be an anomaly. That's what I mean. It's like the thing you're looking for, and that's I was just curious how you begin to discern between those.
Because typically we are really interested in the anomalies, actually, but then it's not, for example, not the point-wise anomalies, because this may be measurement outliers. So but we then try to detect, was this a measurement anomaly? So was the sensor not measuring correctly, or was this really something that was coming from the process? So yes, in this case, we're applying some logics to exclude those that were just sensor anomalies, but then we are more interested in the degradation or in the faulty systems.
It's quite interesting, just what you've just mentioned here. I'm taking the difference between a tunnel boring machine, which is at the size of meters, and circuit breakers, which are not, maybe they're millimeters to centimeters in my mind.
Oh, no, these are the big circuit breakers, actually.
Oh, okay. These are also big mom. Okay. Like in transmission stations and things like that. Okay. Not the ones I have at home, like the little.
No.
Okay. But still, that's quite a range.
Still, we have different sizes of systems that we're looking into. And for example, we also look into bearings of small systems, but we also look into bearings of wind turbines that are actually huge. So,
so with your research, I'm just with the methodology and how you're thinking about it, does it matter whether, or can it be applied to something which is meters in length and nanometers in length, or is it really more, is it more the focus on, say, the meter plus or centimeters plus?
Well, it actually, so one of the projects that we started some time ago is about learning the interaction between particles. So then it's quite on a small scale actually, but there we are learning from simulated data. But in general, if you want to detect something, then it's rather about the resolution of the data. So is the sensor resolution enabling us to capture the relevant processes or the relevant deviations that we would like to detect? So we haven't yet looked into nanometer systems or micrometer systems. Because they are possibly there, the sensing devices need to be really sensitive to those. But yes, so it's more about sensing and data resolution than about the size of the systems.
Okay, that's cool. So this is a slight change of tact. When you were 12, you woke up one day and you said, I can't wait until I can detect anomalies in tunnel boring machines. And now, X number of years later, you're there. Is that correct?
Well, not quite, actually.
Okay. Well, fill in a little bit. What brought you to this fascinating domain?
Actually, during my master thesis, I started dealing with availability predictions and availability analysis. So back then it was on chemical production plants. Mm-hmm. And then I was quite fascinated by the methodology, but I was not yet applying any type of learning algorithm. So this was pure math, actually. Mm-hmm. And then I started working for a train manufacturing company, doing the same type of things, or the same type of tasks, or availability analysis. And after that, I actually changed then, was started a PhD at ETH, and I was still not yet in this machine learning and neural network topic. Mm-hmm. I kind of started exploring different topics and what other researchers did. And I was nearly already on the way to a bit different direction on my PhD, but then I read one paper actually, and that one was dealing with predicting faults of trains with neural networks. And I was really fascinated by that paper, and I then started exploring what others did in that field and how this could be applied. And this is when the journey has actually started, and then I adjusted the direction of my PhD, and then since then I didn't do anything else actually.
So you got bitten by the neural network bug, which is good. Which is actually quite fascinating. You know, when you kind of look at that. So if you look back, what has been the most significant change in say in the past? I guess that would have been say 10 years ago. In the past 10 years from when you bit the bug, what has been the biggest change?
On the one hand, well, there have been a lot of changes actually. So deep learning emerged and has become quite powerful. But then also the hardware has enabled to do that. But then also more and more data has started to be captured. So when I started, it was still quite difficult to get access to data, but now it's rather, well, at least for us, it has become rather easier to get access to data. But what has really changed as well is the acceptance of the methodology by the decision makers. So when I was a PhD student, it took me quite a while to convince people to share data with me and why it's important, what I was going to do with it. And they did not quite trust that something could come out of it at all. But now it's actually rather the other way around, that a lot of decision makers believe that there should be something that could be done with it, and the data contains quite a lot of information. So it's rather our task then to find out what type of information the data contains. So you know, the expectation has changed quite differently.
So if you think 10 years into the future, because we're going to come back to research in just a minute, but if you kind of extrapolate 10 years back, 10 years forward, what do you imagine or hope will be the biggest change, or what do you anticipate as being the biggest change you might see in 10 years, let's say 2030, plus or minus?
I hope that the algorithm that we develop will be able to generalize much better than that they are now, but also that we are able to provide much more interpretability to those algorithms, that they are able to support the decision makers in a better way. But then one of the additional changes that I hope that we'll be able to make is that domain experts and the algorithms are able to interact with each other in a better way, kind of to complement each other and to share tasks where it's appropriate, and kind of to learn from it or to provide support to each other, kind of in both directions.
So if you think about it, has AI and the utilization of neural networks, machine learning, but AI changed how we monitor systems? For example, you said you personally, with your research group, are less involved with the creation of the data sets themselves. So that comes from the sensing, okay? But once you've got the data or the feedback to the monitoring of the systems, has AI changed that in any way? Because it used to be some person going around with a notebook and writing it down, or then we've got the strain gauges which pop out certain things at a certain interval.
Well, particularly these inspections are starting to be kind of automated much more. So we see, for example, drones or walking robots that collect information and that possibly collect more information than a human could. Or there are, for example, these video towers for train systems where the train pass and that are supposed at least to substitute or to complement the inspections that are performed on the freight wagons, for example. So really to detect what is deviating, because it's quite fast that things need to be detected, and then it may be some of the information may be lost or may not be detected. So there have been some changes, or some changes are upcoming possibly. Because a lot of those systems are still in evaluation or are kind of still in the prototype phase, but not in the field completely. So this will change additionally how the systems will be monitored, but also how this information will be complemented by the decision makers. So, for example, for the railway track, there is a track inspector who actually walks along the track and really is supposed to detect faults and anomalies. But partly now it's in parallel, so it's not substituted, but in parallel, the additional cameras that are applied, but the data is collected on the anomalies and faults on the track. So that is from visual inspection, actually. So particularly this visual capturing of information can and is already being automated partly.
So I like that as an example, because very often in built items, there can be corrosion or damage which you cannot see. There's no external manifestation, but there's an internal structural manifestation. And that's where I'd like to believe what you're talking about, with the maintenance, you might be able to begin to detect some of these things, which is a decision support. Am I getting that picture right?
So actually there is another research group, or actually two research groups here at DTH who have been collaborating on that, so to complement just the visual information on the bridge monitoring, additionally by non-destructive testing. And that's exactly what you're mentioning, is that we are not only taking the information, the visual information into consideration, but also additionally kind of augmenting this by non-destructive testing. But obviously there's for that additional algorithms are developed that are complementing the two information.
So I want to come back to some of your research group. So I'm just intrigued by the title, right? Because I know the intelligence is in there, and I know you're working with complex systems and maintenance. And so tell me more, or tell us a little bit more about what some of the other projects are that are really you're excited about, that you're working on.
Well, we actually do two types of projects. And one type of project is rather fundamental research where we are trying to push the boundaries of the methodology, and and those are really motivated rather for the type of questions that we would like to solve. And for example, the type of questions that we would like to solve is how to make their algorithms better transferable between different operating conditions, between different systems, because what we have actually seen is if we apply an algorithm to one system and then apply it to another one that is operated differently under different conditions, but also that has some deviations in the design, then the algorithms will drop the performance actually quite significantly, partly. And in fact, so we have been pushing that direction a bit, but now, for example, quite some interest starts to be emerging in that direction, because companies start to realize that this is also one of the problems that they are facing. So it has been kind of nice to see how this direction of what we believed was relevant now starts to become picked up by the industrial partners as well. Another direction that we work on is prescriptive operation. So that is also one of the directions that we believe that will be relevant soon. But that is also, so the idea there is really to provide recommendations to prolong the remaining useful life. So it's kind of quite exciting direction and quite a promising one, because we could control when the systems would fail and to start kind of influencing that proactively. So for example, if there is a drone that needs to fulfill some tasks, and there is suddenly either a fault happening or different, or the conditions are actually changing, that we try to adjust the load profile, for example, so that the system can still reach the end destination. So that is one type of the projects that are kind of guided by the methodology and by the type of problems that we believe them should be solved or are relevant or will become relevant. And the other type of projects that we're working on are rather driven by industrial applications. So we still develop methodology there further. So typically we don't just take something that we develop or just apply it. There's still quite a lot of research where we need to develop it further. And there we, for example, are collaborating with diesel engine manufacturer of maritime vessels, and we are collaborating with SPB on the railway wheel monitoring, or we are collaborating with the manufacturer of laser coating systems, where we monitor the acoustic or the acoustic emissions of the production system in order to predict the remaining useful life of the nozzle. So it's kind of different type of applications, but still there is quite a lot of methodology development involved, but driven by a concrete problem. The other one is rather driven by the methodology, and then we try then to validate the developed approaches still on concrete applications, on concrete studies, so that we can really demonstrate that the methodology works and can be transferred, but that is rather driven by us, and the other one is rather driven by a concrete problem.
I like that. So this, on one hand, you're evolving what the questions are to ask, and the other side, you're like, okay, we've asked him the questions, now let's find the answers. Like, this is that's kind of cool. It's be able to do both of those. Like, I'm sure they feed into each other quite well, because you discover different things, So in a way, you're like a doctor, help, prescribe what's wrong. And you have to ask, well, you're not asking the right question. Let me tell you the question you need to be asking. That's really kind of cool. I like that. So one person sent a question in, and the question is actually quite specific. So I am going to do what I normally never do, which I'm going to read the question to you, Olga. But I think it's actually quite intriguing. I'm curious. It says, we're developing and providing robotic inspection solutions for industrial sites at antibiotics. At the ATAS spinoff, you probably know them. Our mobile robot collects sensor data, can detect anomalies and faults, but we find it difficult to get the training data to check algorithms and also to identify the appropriate sensor modalities. Do you know of any publicly available data sets for training, for example, cracks, oil spills, etc.? Or are there any plans to create open source data sets so we can train our drones or things like that? It's a very specific question. You can charge him then a fee. You can charge him a consulting fee. Intriguing. Data sets to train, because this is what you mentioned before. There's something with the experience, and that's why I wrote this. So it's like how you're using this for decision support. That experience is that can transfer that to younger staff members who don't have the experience, right? So this is a training aspect.
Actually, this is one of the big problems in our field, that we don't have sufficient fault cases, actually. And then the whole community has been struggling to find ways, on one hand, to tackle this problem, but on the other hand, also to put some of the data sets out there. So we did put some algorithm, some data sets out. So for example, for predicting the remaining useful life, but also for detecting, but not very specifically for the image data. To my knowledge, there is one data set on cracks for bridges that is openly available. But for oil spills and metallic cracks, I'm not aware of. I can double check if I can find something. But one of the messages that I would like to put forward is also that we as community need to start sharing data. Because typically, this is not proprietary data. If we take images or pictures from cracks, and if everyone can benefit from that, I think that will help everyone. Going a bit in that direction and pushing that direction, I believe it would be quite helpful if there is some support from the industry as well. But I've been advocating for that already for a while, and at least I did see some efforts to do that. Some railway companies, including SBB, but also ProRail in Netherlands, have started putting data sets out there, partly on Kaggle as competitions, but then they are openly available. That help on the one hand to push this algorithm development further, but then also to share that among the stakeholders. But then maybe another direction to pursue is not to develop algorithms that learn the specific identification of the fault, but rather going the direction of unsupervised learning. So this was something that we were developing, and or not just us, obviously also some others as well. But instead of learning the algorithm and, for example, defining the problem as a classification problem, we were rather trying to develop algorithms that enable us to learn the healthy condition and then to start monitoring it over time, and then develop health indicators that provide us the information on the health evolution over time. So on the one hand, maybe start this movement, but on the other hand, maybe try to circumvent it by avoiding defining it as a classification problem, but possibly rather going in the direction of unsupervised learning.
So just how hard is it to detect the anomalies in the bearings of a wind turbine? Or I mean, it's just, and this is absolutely not your job. Is it trivial? Is it like ungodly difficult? Is it something in between? Just takes a lot of gut, I mean, where? Help me understand that. Yeah.
Well, it depends also on the severity and on the size of the faults. So, for example, in bearings, this is this is a field where there has been a lot of ongoing research for decades, and it's really not something new. But what has been improving is, for example, the early detection. So how early can we really detect something, and kind of pushing that boundary that we detect the faults even before they become into defects. So that will enable us then to refurbish the systems kind of before the defects have been manifested themselves into the systems. But then also not just detecting the faults, but distinguishing between the different fault types and distinguishing between the different severities. This puts additionally on the challenge. But for example, detecting faults can be performed with signal processing quite well, partly. So there is already quite a high level of performance that can be achieved with signal processing, but going the additional or with the going a bit more to the top, but also trying to detect them as early as possible, distinguishing between severities. This is where deep learning helps, but also transferring models between different systems. That is also something that is has been quite helpful and was supporting the detection process.
So, because it sounds like, as you were describing before, I come back to what you're in the very early part of our conversation about, it's not just about determining the faults, but it's also helping to understand what we can do about them, or what someone can do about them. That's what you're extending your work is not just, hey, here's a fault, but here's a fault, and here are some of the, this is a question, not just a statement. Here are some of the things that you can be doing based on our understanding of the fault. Is that fair?
Yes, sir. Providing recommendations on what can be done. This is part of the decision support. But from detecting, we also need to go in the direction of distinguishing between the different fault types. Because, for example, if a technician needs to fix something, but does not have the concrete information what has really happened and which subsystem is affected, so then it's quite difficult then to even support in this case. But providing more guidance that is on what has happened, but possibly also what were the most influencing parameters and what may have potentially caused it, may provide additional support on fixing the problem, but also on repairing and putting it faster back into operation.
Interesting. But that implies here, that you're doing that research to understand the fixes. From a research standpoint, a lot of close and tight collaboration with a research partner.
Well, in this case, yes. So we have not been working that much in that direction, but there are some other research groups that have been analyzing, for example, the maintenance reports, and we're trying to learn from the maintenance reports. There is a new research direction that is not called natural language processing, but technical language processing, because technical language has some different challenges compared to natural language processing. Because, for example, the terminology and the ontology, so how the terms belong together and how people call actually different parts or what really has happened. So what is the vocabulary that is used and how to map that and how to learn from that. So that has been quite a recent research direction that has been evolving. We have not been active in that, but it's quite an exciting as well. It has quite a lot of challenges also that are linked to different languages as well, and how how different cultures are using those those terms also by describing what has happened and what was really done, because this provides more information on the root causes, but it will provide then additional information later on supporting what can be done, and for example, providing information that this part has failed in a similar way in the past, and this is what has been done. Then it's more easier to fix that instead of possibly looking for some clues and trying to find the information.
I can't get rid of the smile on my face because I'm thinking of the NLP could then now stand for nerd language processing instead of natural language processing, instead of technical. I mean, I'm a bit of a nerd myself, so I kind of like that idea that there's a whole new field just dedicated to us, trying to understand us. So when you're there, I'm coming back to this idea of the transferability, which is to me is really quite intriguing, especially if I think about maintaining a railway, because you started off in chemical processes, which is very complex. It's very complex compared to pouring a concrete column and watching it sit there for a while. I mean, so I think about the transferability and where you would like to try to take your research group, where you imagine pushing that in, because it's fascinating to hear the different domains you're working in, and it seems like it's transferable. It said the size doesn't really matter. Go ahead, sorry.
But we are mainly driven by the methodology, and this is where kind of our excitement also comes from. So if we can push the methodology further, and if we can then solve the problem in different domains, then this is really what excites us. And if the results that we are obtaining can be transferred to something else, that is really exciting. So for example, with the monitoring of the laser coating systems. So this was not something that we were even considering that our type of algorithms would be applicable to, but our project partner, or now our project partner, he has attended one of our talks and on domain adaptation and how algorithms could be transferred between different systems, between different operating conditions. And he kind of got inspired by that, and got inspired that this could be really applicable to his problems. And this is how we started discussing. So partly it's not even us who kind of think where else could it be transferable. But then, for example, we have been discussing also with debris flow monitoring. So basically, they are also using type of data that are quite similar, but also they face the problem that there are not many events that can be detected or that can be learned. So it's very difficult to learn from debris events because there are not many of them. So it's kind of a similar type of data, similar type of challenges that we are facing. So for example, currently we're also looking into this type of data and trying also to perform anomaly detection there. So it's kind of the type of problems that we are facing. I think it's transferable to different domains. And then trying to apply or to transfer this to other domains as well. This has been quite interesting, and particularly those discussions trying to find out if that is really applicable, if this is really the same type or similar type of problems that we're facing as well. This is the joy of research.
Yeah. So how difficult, I mean, is it harder to detect the error or the fault, or is it harder to figure out how to solve it?
It's harder to figure out how to solve it, obviously.
Oh, okay. Well, I was hoping you said, oh, it's easy.
No, but for example, normally the way we try to detect anomalies or deviations from the normal conditions is that we train the algorithm on the normal or healthy conditions, and then we try to detect once they start deviating from those normal conditions. But at least we can define what normal conditions are, or we can also learn what normal conditions are. But then trying to figure out what needs to be done to fix it, there we need to learn from the main experts. We need to learn what has been done in the past. So that is obviously more difficult, and there is also less data to learn from, because, for example, healthy conditions are quite ubiquitous. So there's quite a lot of data that is captured. It's rather those rare events. And if we learn from the examples on how to fix it, then there are very few examples that we can actually learn from. So that's that's obviously more difficult, since we don't have many examples also to learn from. And it's more complex because like different people would also fix it maybe in a different way. So it's also influenced by the human factor. It's influenced by the level of expertise and how they are actually inspecting it. So it's quite a lot of different influences that need to be considered.
So what kind of a problem deserves your attention?
If it's sufficiently challenging, and if there is a potential to develop methodology further, if
okay, you're gonna have to give me a little more on that. Like crossing the road can be a very big challenge, right? And that's not the kind of, you gotta watch out for other cars and get your timing right.
Then normally we are looking into complex systems, and the complex systems are typically monitored by different types of sensors, it's noisy environment, so it's difficult to get clean data. It's also difficult to extract patterns. So then that's when we get interested. But sometimes you also get into discussions with some other colleagues who are working on something else, and even then it's interesting for us. So, for example, this debris flow monitoring, I would not have started thinking about that, but it was evolving from a discussion with a colleague, and then it sounds interesting because it's challenging. It's similar to what we did, so it's still in the field of anomaly detection, but yes, that's also what excites us. But one of the additional directions that excites us a lot is also this hybrid modeling, where we are trying to combine physics-based models with deep learning algorithms. And if we see some potential applications for that, so then it's also quite exciting. And if we can push the methodology further, so that's also what gets us interested.
I'm intrigued by the hybrid model. Can you tell me a little bit more about what that really means? So.
Well, actually, different people use this term for different types of models, or hybrid models can be knowledge-based models combined with data-driven models. It can be, some people even use hybrid models when different types of AI algorithms are combined. But we use hybrid models when we combine physics-based models with deep learning algorithms.
Okay, that makes sense. So what is if you could wave a magic wand and have a project land in your group, what project would be your dream project that you're not doing yet? Like what would just like be, hey, I'd love to work for the next 5 years on this. What would that be?
It's quite difficult to say. So, for example, a grant has been just granted on developing hybrid digital twins.
Cool.
So combining then physics-based models with deep learning algorithms, so to also enabling predictive capabilities, evaluating extrapolation capabilities. So that's really a project that I'm quite excited about. And that we will be working for the next 4 years, and it has already landed in our group. Cool. So I'm really quite excited about that. But there is quite a lot of different aspects into that direction that can be developed further. So every kind of a lot of or everything that is connected to that is would be quite excited to.
That's very cool. No, that's very cool. I congratulations on that. That's really wonderful. And is the digital twin, is the hybrid digital twin sort of like fusion? It's always 10 years away, or is it something which we can now depend upon, seeing and utilizing?
Well, it has quite a lot of promises that will become possible once the methodology will become possible. And one of the promises is, for example, that we are able to detect faults at the very early stage, that we can mitigate them before before they even manifest themselves. But the other direction that is also quite promising is the one of this prescriptive operation. And what we also need for this type of algorithm, prescriptive algorithm, is a very good model that really kind of builds kind of the real operation, but is also has understood the underlying processes, but also the underlying operation. Using that within that framework will provide quite some promising directions that we can develop further.
Pretty cool. I'm very excited about what's to come, especially when you become successful in evolving our understanding of the utilization of data and decision making in these complex systems. Because the challenges we'll be facing as a society are only going to be becoming more complex, more difficult to understand. So this idea of having this decision support, where you're putting the best of everything together, seems to make a lot of sense to me.
It's actually quite. Oh, sorry.
Go ahead.
No, but it's quite exciting to use this information kind of not just as one system, but to build this as a modular approach. Because as you mentioned, the complexity has been increasing quite a lot. Kind of everything starts to become interconnected and also with mutual inter-influencers. So then if we are able to build this system of systems and to integrate this at different hierarchical levels, that's a nice direction to pursue.
But isn't there also a trend? I'm glad to hear you say that, because I agree with you. But isn't there also a bit of a trend towards increasing autonomy of the various systems? And how do we resolve that? Like the autonomy of a heating system versus a lighting system, or of a rail, so an energy system.
Well, actually, those autonomous systems will require a better diagnostic capability and a better prognostic capability. But also, if we can operate them prescriptively, so that is even better. So if you have an autonomous car and then it stops in the middle of the highway, it's maybe not so desirable, but then you will need someone who may need to fix it, and you will need to guide the person to perform the first remediating actions. So that is also something that will probably push our research a bit more, because then the importance will become stronger than. Because we will not have the expert who may be then at the place where the remediating actions may need to take place. So then we will need to guide the non-expert to perform those actions, and possibly also to adjust the level of expertise, or how to provide the guidance depending on how knowledgeable or how experienced that person is. So that's again a bit a different level or a different direction. But that will also be something that research will need to work on.
Now, is it? I hear you, and I think that's really great. Now, are your systems? I'm thinking about, you said the bottlenecks, but are they easy to interface with, or does it require someone with a PhD doctorate
Well, you mean for the decision supports, or I think one of the
Yes.
requirements for the decision support is to provide the information really at the level of expertise, so to a normal operator or to a technician, but then possibly to an engineer at a different level, because the engineer may need to understand the model better, or may ask additional questions. So the decision support will need to provide different type of information. On possibly different type of guidance. So this is really one of the requirements that we need to follow, that they are kind of understandable, easy to follow, but also at the right level of expertise, and providing the right information so that the decision maker can really follow this and trust in the decision.
So we have only 5 minutes left, actually 4. It's gone by really fast, and I would like to ask 1, maybe 2 final questions. And the first one is, if you're standing in 2040, 20 years from now, and you're looking back at what you have achieved, what has changed in the practice of sort of in industry, manufacturing, and maintenance, and what has fundamentally changed? What's the story that you have helped to write when it comes to the industry?
I hope there will be different types of stories. So sometimes that we help to make the models better transferable, better generalizable, better interpretable, and then obviously then better accepted by the decision makers, while at the same time pushing the performance. But I also hope that by that time the prescriptive operation will have taken off, and this is where our current research will gain more momentum, and that we can develop that further. So yes, so these are the directions that I hope I will be proud of in 20 years from now.
Well, I hope you're successful. I actually know you'll be successful. The question is then what degree our very conservative industries will take on board the continued evolution of these new tool sets, right? As you're able to help them see the advantages.
It has been quite surprising, actually, and
really?
but also quite rewarding in the recent year or month even, that our research is kind of getting some attention, and I'll start getting excited about it, and that it's really nice to see, but also very rewarding also to continue.
Well, that's the perfect place to stop. That's really fantastic. Seriously, to hear that and to see the enthusiasm in your face, and to read that in your face, and to hear it in your words about it starting to, as you're saying, starting to be understood as relevant and understood as impactful, and that's really wonderful to see.
Yes.
So thank you very, very much, Professor Olga Fink.
Thank you, Chris, for guiding and for guiding the conversation, for your questions.
It's been a real pleasure, and I want to thank all of you who have tuned in and who will be watching this in due course, to participating in our dialogue. And again, if you haven't already seen the Spotlight with Olga, I encourage you to go and check it out on the AI Center website. And our next Spotlight and our next series is going to be on AI and retail, and that will be with Professor Xiu Tang, and that will be released in August. We've already shot it, and it's going to be quite interesting for you to check it out. So stay tuned. Please check out the previous spotlights and dialogues on the AI Center website. And I want to thank Fiona for helping out, Fiona Kuntz, and my team for helping out, and Klaus and Alex at the AI Center for your faith, and the ETH Zurich for the continued support of your research, Olga, us, and making the world a better place. So with that, I wish everybody a wonderful day. And Olga, I hope you have a great summer.
Thank you. Same to you, Chris.
Thank you. And we'll say ciao, ciao. Goodbye, everybody.
Bye.
Ciao, ciao.